So how do we balance equations? So here are the instructions, and then we'll do some examples. You start out with a skeletal equation. And what you need here is you need the correct chemical formulas for the reactants and the products. So identify, okay, what are the formulas of the reactants? And we'll put those together, pluses between them. And then we've got the arrow, and then here are the the product formulas. Very important that these formulas are correct. Oh, that's not a good color. Correct chemical formulas. If your formulas are incorrect, you're going to have trouble. Okay, chapter 5 is where we learned about that. Then what we're going to do is it's called balancing by inspection, which means you look at it and you balance it. And there are different approaches. So we can kind of give you a guideline for how to approach it, but there's no hard and fast rule. So one guideline is that if there's an element that occurs in only one compound on both sides of the equation, do that one first. If there's more than one, balance metals before nonmetals. So some of you might appreciate that guideline, and if you just ignore that, it's usually okay. If an element occurs as a free element on either side, meaning it's all by itself, like in the previous example, we had oxygen as a reactant. It's just oxygen. You generally want to use that one last, because when you fix that one, it doesn't mess up anything else. Sometimes you end up with fractions in your coefficients, and if you end up with that, then you need to get rid of them by multiplying everything. We'll go over that. At the end, double check. Add up the total number of atoms of each element on each side and make sure that you did it correctly. So these are important. Do change the coefficients. Coefficients are the numbers in front of the equation. You can say, okay, well, I need 2 oxygen molecules, or I need 4 oxygen molecules. That is the correct way to balance equations. Do not change the formulas themselves. Don't change the subscripts. You can't say, well, if it was just O, then it would balance, so I'm just going to get rid of the subscript 2. Well, that's the chemical formula. You can't change what the chemicals are. So let's do some examples. Write a balanced chemical equation for the reaction between solid copper and solid sulfur to form solid copper 1 sulfide. So some of the questions, they're going to force you to practice your nomenclature by giving you names of the compounds instead of the formulas. So here we've got solid copper and solid sulfur. Those are elements, right? So one of our reactants is copper. It's giving us the state. So that's a suggestion that we should probably include the state. So copper, solid. That's reacting with sulfur. And it's telling us that that's a solid. Those are both elements. Then you always need to check, are either of those diatomic elements? Horses need oats for clear brown eyes. No. So then they're just the element symbol. If they're diatomic, then you have to put a subscript 2. Now when I wrote those, I left a little space here because I might need to put a coefficient in here. So solid copper and solid sulfur to form. That's the arrow. They're forming solid copper 1 sulfide. We need the formula for that. Copper 1 is Cu+. Sulfide is S, and what's the charge on it? -2 on the periodic table. 0, -1, -2. So to put those two together, we're going to end up with Cu2S. And it says that's a solid. So we wrote the correct formulas for our reactants and products. That's the first thing. This is a skeletal equation. And then we need to balance it. So here's one approach for balancing. So I'm just going to draw a line at the arrow, And so this is like my teeter-totter. So that's the balancing point. And then over here on the left, I'm just going to list the different elements that I have. I have copper and I've got sulfur. And I'm just going, starting left to right and reading across and writing down the elements that I come across. And so then I'm going to make sort of an inventory of what I've got. And this is overkill on this one. This one's a simple equation, but it's a technique that is useful at times. So in this formula, how many copper atoms are there? 1. How many sulfur atoms? 0. This isn't sulfur, that's a solid. And then over here, I've got 0 coppers and 1 sulfur, right? So if I total those up, on the left side I have a total of 1 copper atom and 1 sulfur atom. You're like, duh, I could see that just by looking at it, whatever. Now over here, in this formula, how many copper atoms? 2. And how many sulfur atoms? 1. So our total over here is 2 copper atoms and 1 sulfur atom. 1 on that side, 2 on that side. It's not balanced. So we need to do something. We're going to add. We're not going to take things away. So we need more coppers on the left side. We can't change the formula. All we can do is put a number in front of it. We say, well, I guess we need 2 of those, right? So we put a 2 in front. That changes our tallies underneath. Now I've got 2 coppers. I still have 0 sulfurs. And that changes over here as well. Now I have a total of 2 coppers on the left side. Didn't change anything on the right side. Didn't change the sulfur at all. But I'm just keeping track down here. So when I put a 2 in front of this, it multiplies everything there. There's only one thing there, but it multiplies everything there. So I've got 2 coppers and no sulfurs here, no sulfurs and 1 copper here. So I've got a total of 2 coppers and 1 sulfur on that side, 2 and 1 on this side. That's the balanced equation. Any questions? Let's do another one. Balanced equation for the reaction between sulfur dioxide gas and oxygen gas to form sulfur trioxide gas. So they're giving us a sentence description. So we've got sulfur dioxide and, that's the plus, oxygen gas to form, that's the arrow. Sulfur dioxide plus oxygen forms sulfur trioxide. So we need to write the formulas for these guys. Sulfur dioxide. Well, that's one of those covalent compounds, sulfur dioxide. Di tells us 2 oxygens. We're given the state symbol, so we should just write that in there. Plus, leave a space. Oxygen. Is oxygen a diatomic element? Yes, it is. So its formula is O2. To form sulfur trioxide. So that's SO3. And we're told that that is also a gas. So that's from chapter 5, taking names and writing chemical formulas. So now I'm just going to look and see what I've got here. Again, we've got 2 elements, sulfur and oxygen. Over here, in this formula, I've got 1 sulfur and 2 oxygens. So I've got 1 sulfur and 2 oxygens. In the O2, there's no sulfur, so I'll write a 0 in that row, and there's 2 oxygens. So if I total those things up here, on the left side I've got 1 sulfur and 4 oxygens. On the right side, I have SO3. That has 1 sulfur atom and 3 oxygens. So a total of 1 and 3. And then I compare my totals. 1 sulfur, that's good. 4 and 3, not good. I've got 4 on the left, I've got 3 on the right. I can't take away from the left, I can only add to the right. So to get more oxygens over here, the only thing I can do is say, well, there must be 2 of these molecules then. I can't change the subscript, because then it wouldn't be sulfur trioxide anymore. So I put a 2 in front of that guy. So I'll put a 2 here. That changes the number of sulfurs and oxygens. Now I've got 2 sulfur atoms and I've got 6 oxygen atoms. So then my totals over here are different. I've got 2 sulfurs and 6 oxygens. Now that might look like we made things worse rather than better, right? Because now we screwed up the sulfur as well. It has to be done. So let's go over here now and do what we can to fix things up. So here we have sulfur and oxygen together in a compound. Here we have oxygen by itself. I don't want to mess with the oxygen first. I want to wait till the end for that one. That's what it means by if there's a free element on either side, save that one for last. Because I could balance the oxygens by making 2 of these, right? And I could fix the oxygens, but that's not going to fix the sulfur. And when I go over here to fix the sulfur, it's going to screw up the oxygens again. So I'm going to leave this guy to the end. I'm going to fix the sulfurs first. So I need more sulfurs on the left side. So the only thing I can do is put a number in front of SO2. There must be 2 of those. That changes the number of sulfurs to 2 and the number of oxygens to 4. Because it's like having 2 bicycles. You've got you've got 2 frames and you've got 4 wheels on 2 bicycles. SO2. The oxygens are the wheels. So that changes our totals. Now I've got 2 oxygens and 4 plus 2, 2 sulfurs. 4 plus 2, 6 oxygens. I fixed the sulfurs, and what do you know? The oxygens took care of themselves. Sometimes they do, sometimes they don't. But now I have a balanced equation. Any questions?
Why did you start on the right-hand side as well versus the left?
Why did I start on the right-hand side versus the left? Because originally I had too few on this side. Originally I had 1 sulfur. It was the oxygens that were messed up. I had 3 oxygens on this side and 4 on that side. And I can't take away, so there's nothing I can do to the left to get more oxygens on the right.
Okay.
I can only add. You can't subtract. So that's why I started on the right. That's a good question. Any other questions?
One more. So on the oxygens on the left, the 2 equals the 6.
That's 4 plus 2.
4 plus 2. So you just added. Okay.
Yeah. So this column here,
Right.
I maybe should come up with a better way to draw it under here. But that's my total for the whole left side.
Okay.
So here I've got, in this guy right here, in this reactant, I've got 2 sulfurs. Over here I have no sulfurs, so on the left I have a total of 2 sulfurs. I have 2 times 2, 4 oxygens here. That's what I wrote down here. And over here I have 2 oxygens. And 4 plus 2 equals 6.
Just wanted another reason.
Yeah, well, you got to make sure that you really understand. And when we first go over it is the time to really understand, right? So I appreciate questions. Let's see. Another example, aqueous hydrochloric acid and solid manganese for oxide forming aqueous manganese 2 chloride, liquid water, and chlorine gas. So we need the formulas for these guys. Hydrochloric acid. The hydro tells us it's just hydrogen and another ion. So that's HCl. HCl, oh, I don't want to do that in pink. HCl, and we're told that it's aqueous, so I'm going to put AQ back here. Solid manganese 4 oxide. Well, manganese 4 is Mn4+, and oxide is O2-. Now, this is one of those situations where you can't just blindly do the crisscross thing, because if you crisscross these, you're going to end up with Mn2O4, and that's not the lowest ratio of subscripts. We need the lowest ratio for ionic compounds. It'd be MnO2. So that's our second reactant, MnO2, and that's a solid. To form aqueous manganese 2 chloride, manganese 2, Mn2+, chloride Cl-1. So that gives us MnCl2. And it says that's aqueous, so I'm going to leave a space, MnCl2, aqueous. Liquid water, we should know the formula for water. And chlorine gas, Cl2. Yeah. Didn't plan ahead very well. Chlorine is a diatomic element. Horses need oats for clear brown eyes. Chlorine. So that's why I wrote Cl2. So now we have all of our things in place. This one's a little more complicated, isn't it? Yeah, just a tad. So we've been practicing our tally method, so we'll keep going with that here. I'm going to go left to right and just write down the different elements that I have. I've got H, I've got Cl, I've got Mn, and I've got O. 4 different elements this time. In that first compound, HCl, I have 1 hydrogen atom and 1 chlorine atom and no manganese and no oxygen. In MnO2, I have 0 hydrogens, 0 chlorines, 1 manganese, and 2 oxygens. And then I'm just totaling these up over here. So I've got a total of 1 hydrogen, 1 chlorine, 1 manganese, and 2 oxygens on the left side. Now I'm going to go look at the right side. In that first compound, I have 0 hydrogens and 2 chlorines and 1 manganese and 0 oxygens. In water, I've got 2 hydrogens and 0 chlorines and 0 manganese and 1 oxygen. In Cl2, I've got no hydrogens, 2 chlorines, no manganese, no oxygens. And I'm going to add these numbers up to see what my totals are. I don't have any space on the left, so I'll write them on the right. 0 plus 2 plus 0 is 2 total for hydrogen. And a total of 4 for the chlorine, total of 1 for the manganese, and a total of 1 for the oxygens. So in here, this is my comparison for the left and the right side. So the only thing that's balanced is the manganese. I find a lot of times it just works to start at the top and work your way down. If you do that and it seems like you're running in circles and like it's being way too hard, then you go back and you start over with something else. That's just kind of the practical approach. Start somewhere. If that doesn't seem to be working, start somewhere else. Because there are easier and harder ways to approach balancing many equations. And there's no point in doing the hard way if there's an easy way. So let's just look at the hydrogens. I've got 1 on the left and 2 on the right. So I can fix that by making more on the left. So I go over here to the compound that has hydrogen in it, and I just say, well, what if I have 2 HCl molecules? That's going to change what I've got down here, which is going to change my totals in the middle here. So now I've got 2 hydrogens and 2 chlorines. So now I've got the right number of hydrogens, the same number on each side. So that's good. Now I can go look at the chlorine. And the chlorine's messed up, isn't it? I've got 2 on the left and 4 on the right. Okay, I can't make the right side less, so I have to make the left side more. Well, the only thing I can do is to change the thing that I just changed, right? So I'm going to take off that 2, and I'm going to make it a 4. Why 4? Because I'm trying to get 4 chlorines. I had 2 before. If I put a 4 here, now I've got 4 chlorines, I'm writing with the eraser, 4 chlorines and 4 hydrogens. Is that making sense? I fixed the chlorines now. I've got 4 and 4, but I screwed up the hydrogens, right? This happens. Let's go and see if we can fix the hydrogens. Now I've got 4 on the left and 2 on the right. I need to go over here to where the hydrogens are on the right side and say, well, if I had 2 water molecules, that would give me 4 hydrogens, and that would fix my hydrogen problem. So I'm going to put a 2 in front of this, and that's going to change everything underneath it. So I'm going to get 4 of those and 2 of these guys. So I've got a total of 2 oxygens now and 4 hydrogens on the right side. This is a very tedious way to balance equations. But when you're first starting out, it's also very thorough and helps you to keep track of what's going on. After you do this a couple times, some people may not need to do it at all. Others may need to do it for quite a while until it really starts to make sense to you what you're doing by throwing these numbers into the equation. Now let's look at these. Okay, this one's 4 and 4, 4 and 4, 1 and 1, 2 and 2. Ta-da! It looked a little ugly there for a while, but we kept going, and then it just cleared up suddenly. So that's our balanced chemical equation. Any questions?
I have a request.
A request.
Can you have this lecture up by this weekend so that we
Yes, I can put it up before I leave today.
not necessarily?
Well, no, but otherwise I'll forget.
Okay.
So I'll just put it up right away. Yeah, I'll get it up as soon as I can. It does help. And I've been a little delinquent on that. In which case, you need to remind me. Yes, remind me when I don't post things promptly. Here's another one. Write a balanced equation for the reaction between liquid benzene. They give you the formula because that's not a compound that we've learned how to name. Benzene is C6H6. And gaseous oxygen to form carbon dioxide and liquid water. So again, we're going to write the formulas for the reactants and the products. So benzene is C6H6, and we're told it's a liquid. It's reacting with gaseous oxygen. Oxygen is one of the diatomic elements, so it's O2. And it's in this writing of equations that is probably the most important. Remember those 7 diatomic elements, because otherwise mastering chemistry will not be happy with you, or maybe you won't be happy with it. To form carbon dioxide, CO2, di meaning 2 oxygens. It didn't give us the state for carbon dioxide. It doesn't give us a temperature. If there's no temperature specified, assume room temperature. What state is carbon dioxide in at room temperature? It's a gas, okay? They're kind of hoping that you might know that by now. So that's a gas, and liquid water, it says. So H2O, liquid. What kind of a reaction is this? Something reacting with oxygen. Combustion. This is a combustion reaction. Okay, so let's do our little thing down here. We've got carbon, hydrogen, and oxygen. In the benzene, we have 6 carbons, 6 hydrogens, no oxygens. In the oxygen, we have no carbons, no hydrogens, and 2 oxygens. When we add those up, we get 6, 6, and 2. Over here, CO2 has 1 carbon, no hydrogens, 2 oxygens. Water has no carbon, 2 hydrogens, 1 oxygen. I'm going to add them up on the left because that was kind of convenient last time. So 1, 2, and 2. So this is where I'm keeping track of what's on each side. 3 oxygens, thank you, because I can't add. 2 plus 1 is 3. I'll have to remember that. Thank you. Did I do anything else wrong? I was just testing you. No, I wasn't. Okay. Let's start with carbon. One carbon on the right, 6 on the left. We can't do anything to make the 6 less. We can only bring the 1 up. So if we put a 6 in front of CO2, that will give us 6 carbons. So now we've got 6 carbons, doesn't change the number of hydrogens, and now we have 12 oxygens, right? Because 6 CO2s, there's 2 oxygens in each, and we have 6 of them. 6 times 2 is 12.
Isn't it 13 oxygens?
We have 12 from the CO2. Yes, that is a good point. So now I'm going to adjust my totals. I've got 6 plus 0 is 6, and down here I have 12 plus 1. I have a total of 13 on the right side. But I set out to fix the carbons, and I did that. Now we need to fix the hydrogens. So I've got 6 on the left and 2 on the right. I need to do something to this guy, which is the only one that has hydrogen, in order to make there be 6. So if I multiply this by what? I need to multiply by 3. 3 times 2 is 6. So then I've got 6 here. That does change the oxygens, and now I have a total of 3 oxygens from the water molecule. So now I go to the middle and fix these. So for hydrogen now I have 6, and for the oxygen I have 15. Don't be afraid of the big number. Okay, sometimes we end up with some big numbers. It's okay. Now I've got the carbons, the hydrogens set up, the oxygens are screwed up. But this is okay because I've got this O2 all by itself. I can mess with this guy without messing up the carbons and the hydrogens. So these oxygen atoms are coming in pairs. How many pairs so that I can have 15 oxygen atoms? Not a whole number, right? Not a whole number. What do we do? I call this the odd-even problem. Okay, the right side is telling me I need an odd number of oxygen atoms, but they're only available in pairs. So the simplest solution to this is to double everything. Because when you double an odd number, you get an even number. There's other ways to do it involving fractions and stuff, but most people don't really like fractions, so we're going to do it this other way. So what I'm going to do is, except for the oxygen, because this guy, this is what I recognize that I need to mess with. I'm going to double the subscripts on everything else. So C6H6, that was a 1. I'm going to make that 2. I'm going to leave the oxygen alone. I'm going to change this 6 to a 12. Again, don't be afraid of a big number. I'm going to change this 3 to a 6. So now let's assess the damage down below. In 12 CO2s, I have 12 carbons, still 0 oxygens, 0 hydrogens, and 24 oxygens. Over here, I now have 2 times 6, or 12 hydrogens, and 6 oxygens. You following me? So then, over here in my totals, I've got 12 and 12. And down below I have 24 plus 6, which I'm pretty sure is 30. Now on the left side, let's fix this up. So 2 C6H6s. That means I have 12 carbons and 12 hydrogens. Didn't affect the oxygens. So then I'm going to go and fix this guy up. 12 and 12. I left this O2 here alone because he was messed up to start with, and we're just going to deal with him at the very end. So by doubling everything except the O2, my carbons and hydrogens are still balanced, but now I need 30 oxygens, which is an even number. That means I need 15 O2s. So if I put a 15 in here, that'll get me 30 there and 30 here, and it will balance. This happens a lot in these combustion reactions with carbon and hydrogen. It happens a lot. Any questions? Yes? If you want to see the other way, yeah. Any questions about this setup before I erase it? So I'm going to get rid of all of this down here. Okay, so while I'm at it, I'm also going to show you the less writing out way of doing this. Let's fix that arrow because it's looking pretty sad. So I'm going to just eyeball this one, balancing by inspection without writing a bunch of stuff down. So I'm going to look over here and I'm saying, well, let's start with the carbons. Here I've got 6 carbons, and then I'm looking at the total on the other side. Like, okay, I've got 1 carbon here. So if I put a 6 there, my carbons will be good, 6 and 6. And then I look over here and I'm like, okay, hydrogens, I've got 6. There's no hydrogens here. Over here there's 2. If I multiply this by 3, I'll get 6 hydrogens, and that didn't mess up my carbons, so I've got carbons and hydrogens taken care of. Now I'm going to look at my oxygens. And here I've got 2 times 6 is 12. And over here I've got 3. And that gives me 15 oxygens on the right side, and they come in pairs. Well, what if I multiplied by 15 halves? If I had 15 halves times 2 would give me 15, right? So now this is balanced, but it's got a fraction in it. So then we clear the fraction by multiplying everything by the denominator of the fraction. The denominator is 2, so I'm going to multiply everything by 2. That becomes a 2. This becomes just a plain old 15. This becomes 12. And that becomes 6. Same result, different approach. Some of you might say, oh wow, that was so much easier. And others might say, oh my goodness, don't ever tell me that again. Right?
So
Yes?
how did you decide that it was going to be halves? Because there's 2 oxygens on the left? Is that why? Or?
Yeah, because my oxygens are coming in pairs.
Yeah.
That was a 3 there.
If it was O3, then I would have done 15 thirds, which would have been 5.
Yeah.
Yeah.
Okay.
So what I was doing is like, okay, X, yeah, let's not even go there. But I'm looking for that combination. What can I multiply 2 by to get 15? You could have put 7.5. 7.5 times 2 is the same as 15 halves. And then you still have to multiply to get whole numbers. Yes?
So if it was just say a third, so 15 thirds,
Mm-hmm.
it would be 5 O2s. Would
Right.
you still multiply everything by 3 or just stop at the fraction there?
Well, if you put a fraction 15 thirds, you can actually just simplify that,
Go to 5, yeah.
right, without multiplying to clear it. But 15 halves ends up being 7.5, which is not a whole number, and that's why we have to multiply. Equations can be balanced without being whole numbers, or without being the lowest whole numbers. But the best form of the equation is the lowest coefficients that are whole numbers.